Welcome to the deep dive. Okay, today we are strapping in for a ride. A ride so fast, honestly, you might start questioning what ground travel even means anymore.
Yeah. We are diving into this massive global race, billions of dollars pouring into ultra-high-speed rail.
And the sources we've looked at, they point to something almost unbelievable. We're talking ground transport that's not just catching up to planes, but in some cases actually outpacing them.
Yeah, the typical speed of a commercial jet, around 885 kilometers an hour, maybe 550 miles per hour. Some of these trains are aiming right for that or beyond.
And that's really the core of this deep dive, isn't it? How is this possible? So our mission today, dissect 8 of the world's fastest trains. We're going to focus heavily on the really revolutionary stuff, especially maglev,
Magnetic levitation, yeah.
but also dig into the surprising details, things like, precision, safety, even silence in traditional high-speed rail.
Yeah.
It's redefining perfection.
And it's crucial to understand this isn't just about speed records for the sake of it. It's a massive technological, maybe even geopolitical contest,
Right?
primarily between, say, China and Japan. And the outcome, it's going to reshape infrastructure globally. It'll fundamentally change what you, the listener, expect from getting between cities.
It really is a shortcut to tomorrow's commute. Okay, let's get into the physics then. To hit these insane speeds on the ground, you absolutely have to beat friction. That's the big one.
Which brings us straight to maglev, magnetic levitation, no wheels, no track friction.
And the most extreme example of this comes straight out of China.
You mean the T-Flight project. That's
Yeah.
the one where, they're thinking less train, more, low-altitude projectile.
Exactly. The potential speed they're talking about is frankly staggering, up to 1,000 kilometers per hour.
Right.
To put that back in perspective, a Boeing 737 taking off, that looks slow compared to this train's potential cruising speed.
So how do they even attempt that? Well, it boils down to 2 huge engineering leaps. First, obviously, the maglev itself. The train floats, 0 physical friction.
Okay.
But the second part, and this is the real game changer, is the plan for vacuum tubes.
Okay. Less air resistance.
Or almost no air resistance. That's the primary speed killer for conventional high-speed rail once you eliminate track friction.
Right.
So the T-Flight travels inside these tubes almost airless. Minimal resistance. It's basically the same principle that lets spaceships move so fast in the vacuum of space.
And if they manage this commercially, the impact is just huge. Think about Beijing to Shanghai.
Yeah.
Right now, the fastest wheeled trains take about 4.5 hours
Yeah.
with this. Theoretically, under 2 hours.
That shrinks the country.
But let's play devil's advocate here. A massive nationwide network of vacuum tubes. That sounds impossibly complex, impossibly expensive to build and maintain.
Yeah.
What are the sources saying about the reality check?
That's the multi-trillion-dollar question, isn't it? The sources absolutely confirm the complexity is immense. But so is the commitment. This isn't just theory, it's tested science now.
Okay.
Newsweek reported on trials at the Donghu laboratory. They hit speeds over 620 miles per hour in tests last year. That's faster than most commercial jets fly.
Wow. Over 620 miles per hour.
And they also managed incredible precision, getting the train positioned with 4-millimeter accuracy, which at those speeds is absolutely vital for safety. They're using AI-guided suspension systems to manage it.
So it's about perfecting the tech now, aiming for commercial use later down the line.
Pretty much. The current reality is still the Shanghai Maglev to Pudong Airport. That's the world's longest commercial line. Runs at about 267 miles per hour, which is still incredibly fast.
Killer fast, yeah.
But the long-term goal, it remains this nationwide network, connecting major cities in, say, 90 minutes or less. That's the ambition.
Okay, so China's setting a very high bar. But they're not the only ones playing the maglev game. Let's shift over to Japan, their L0 series. If China's big bet is on vacuum tubes, what's Japan's angle with their maglev?
Japan's focus seems to be more on, let's say, control and proven precision, using a different core technology. Superconducting maglev.
Superconducting?
Yeah, they use incredibly powerful superconducting magnets. The trials have also hit amazing speeds, 603 kilometers per hour, and their train floats higher, a full 10 centimeters above the track.
10 centimeters?
Yeah, which requires serious cryogenic cooling for those magnets. It's a different kind of extreme engineering.
Okay, and the real-world impact. When do we see the L0?
It's scheduled for initial service in 2027, and the big prize is Tokyo to Osaka. Right now, that's about 2 hours, 15 minutes by Shinkansen.
Okay.
The L0 will cut that down to just 67 minutes.
Wow, less than half the time.
Exactly. And when you slash travel time between two major hubs like that by over 50%, you're not just competing with cars anymore. You're directly replacing domestic flights. It changes everything. So while these maglev projects, they capture the imagination, floating trains, near supersonic speeds, we absolutely have to talk about the incredible engineering happening with traditional wheeled high-speed rail, too.
Right, because wheels on steel isn't dead yet. Not by a long shot.
Far from it. And these trains, maybe they don't float, but they operate with a kind of reliability and safety that, frankly, much of the world is still striving for.
And this is where that idea of fastest gets really interesting. Because raw speed doesn't mean much if the train is always late or, worse, unsafe.
Exactly.
Which brings us to our third nugget, the absolute gold standard for reliability. Japan's Shinkansen, specifically the E5 series, commercially, it only hits 320 km/h.
Only. Still very fast.
Yeah, right. Still incredibly fast.
Yeah.
But its real power isn't just the speed, it's, well, perfection.
And we actually have a number for that perfection. The source material highlighted this detail, and honestly, it just blows my mind every time. The average delay for the Shinkansen, 18 seconds.
Per year.
Per year, across the entire network.
That's not a transportation metric. That's like a Swiss watch metric.
It's almost unbelievable. 60 years they've been running the Shinkansen. 60 years on an 18-second annual margin of error.
And 0 fatal accidents in all that time.
0. That's the baseline for perfection in global transport now, set by Japan decades ago.
And they're green too, right? The braking system.
Oh, yeah. Highly efficient regenerative braking. Like in an electric car, when it slows down, the motors turn into generators.
Capturing energy back.
Exactly. Feeding power back into the grid. The sources noted it's so efficient. On downhill sections, the E5 can actually produce more electricity than it consumes.
Okay, that's genuinely impressive. Now, China's not only doing maglev, they're pushing conventional rail hard too. Yeah. Let's talk about the CR380D. The sources called it the silent ghost. Why?
Hey, yeah, the silent ghost. That nickname comes directly from how quiet it is, even at speed. This was a big deal, the first high-speed train built entirely with Chinese tech, not based on German or Japanese designs.
Ah, okay. Homegrown innovation.
Right, and that distinctive dragon head nose.
Yeah.
It's not just for looks, it's pure obsessive aerodynamics. Engineers were apparently amazed. You can stand near the tracks, and as it flies past at over 350 kilometers, you barely hear a whisper.
Wow.
They managed to smooth the airflow over the chassis so well, it virtually eliminated that typical whoosh sound generated by air resistance at high speed.
Wow. Okay, and then there's its sibling, the CR2 380A. This one's built for endurance.
Yeah, that's the long-haul champion. It hits 420 kilometers in tests, but it's really designed to just stay fast.
How so?
It uses advanced liquid air cooling systems. This lets it maintain speeds over 350 kilometers for hundreds and hundreds of kilometers without overheating or needing to ease off.
Right.
And crucially, it gets its electricity supply while moving from overhead lines. No need for long technical stops to recharge or refuel. It can just keep going.
So it's a direct challenger to domestic flights within China.
Absolutely. Covering huge distances, city center to city center, potentially faster and definitely more comfortably than flying.
Okay, let's hop over to Europe now. The focus seems to shift slightly again. Germany's ICE-3. Top speed around 300 kilometers operationally. But the big claim is safety. They say it's practically impossible to derail.
That is a bold claim, but yeah, there's serious engineering behind it. Two main things contribute. First, distributed traction.
Okay, what's that?
Instead of one big locomotive pulling or pushing everything, the power units, the motors, are spread out under multiple carriages along the train.
Ah, so power comes from multiple points.
Exactly. It makes the whole train inherently more stable, more balanced, less like dragging a heavyweight, more like the whole thing is pushing itself evenly.
Gotcha. And the second thing?
An active tilting system. This lets the train lean into curves, sort of like a motorcycle. It counteracts the centrifugal force so it can take bends at much higher speeds while passengers barely feel it, and crucially, it maintains stability. Sensors constantly read the track ahead, so the tilt is proactive, not just reactive.
Speed and safety working together.
That's the goal. Plus, obsessive aerodynamics, like the Chinese trains.
And finally, Italy. The Italo AGV. What's its innovation?
Structure and materials. Like the ICE-3, it ditches the traditional locomotive design. Power is distributed throughout, but it also uses lots of ultralight composite materials.
Making it lighter, so faster and more efficient.
Precisely. Allows it to accelerate quicker, use less energy, hit high speeds 360 kilometers in tests. But the real standout for passengers, according to the sources, is the ride smoothness.
How so?
Advanced suspension and damping systems that apparently eliminate almost all vibrations, even at top speed. It proves that smart design with modern materials can deliver speed, reliability, and a really premium, comfortable experience.
So we've seen silent giants, almost impossibly punctual machines, trains that literally float. Where does all this innovation lead next?
Well, that brings us back to Japan and their next big experiment, the Shinkansen Alpha X. This is seen as the blueprint for the future, maybe hitting service around 2030.
And it's fast.
Oh yeah, 400 kilometers in tests. But the truly mind-blowing part isn't just the speed, it's the adaptive technology. It's less a static machine, more a dynamic system.
Meme.
It's constantly analyzing data. Over 10,000 data points while it's moving, monitoring everything from external temperature and wind to internal vibrations and adjusting itself in real time.
Wow. And the most visible part of that is the nose, right? That incredibly long nose.
22 meters long. And yeah, it's not just for show or even just basic aerodynamics. The sources say parts of it can actually change shape automatically.
Change shape? How? Why?
Sensors detect things like strong crosswinds or the pressure waves when entering a tunnel. The nose subtly adjusts its form to optimize airflow, maintain stability, and reduce noise, especially that sonic boom effect tunnels can create.
It's like dynamic aerodynamics, adapting on the fly.
Kind of like the control surfaces on a fighter jet, but applied to a ground vehicle reacting to environmental conditions.
That's incredible. And the safety systems for something moving that fast must be off the charts.
Absolutely. Its emergency braking is apparently setting a new standard. It can bring the train to a complete stop from 400 kilometers in just 2 minutes.
2 minutes from 400. How?
Using a combination of traditional brakes, air brakes, like flaps, and even magnetic track brakes that interact directly with the rails.
So, okay, stepping back, looking at the big picture, what does all this mean for you, the listener, down the road? It feels like this shift away from just relying on wheels and friction towards magnetic levitation, maybe even vacuum tubes.
Yeah.
It's really picking up speed globally.
It absolutely is. And you see this fascinating race playing out. On one side, you have, say, Chinese ambition aiming for these truly unprecedented speeds, literally flying through tubes.
Right.
And on the other, you have Japanese perfectionism focusing relentlessly on engineering reliability, achieving that near-zero delay, total safety record, even if the top speed isn't quite as high as the theoretical Maglev maximums.
So the question isn't if these super trains will start replacing planes for those medium-distance trips.
No, the sources really suggest that question is settled. It's now about how quickly that transition happens. The ground travel revolution isn't coming, it's already here, and it is seriously fast.
We've covered some amazing ground today. From trains that run with near-perfect punctuality, measured in seconds per year,
Incredible.
to machines that float, that adapt their own shape, that aim to fly through vacuum tubes faster than jets. It really is this global push redefining what speed and safety mean on the ground.
And, given that incredible focus, especially from Japan, on punctuality, that 18-second metric, and the focus from Italy and others on passenger comfort, eliminating vibrations, smooth tilting, it raises a really interesting final thought. Will the ultimate definition of fastest actually shift away from just the top speed number? Could the global standard become less about hitting the 1,000 kilometers and more about the capacity to deliver an absolutely predictable, totally seamless, utterly frictionless journey from A to B?
So fastest means most reliable, most comfortable, most predictable.
Perhaps. What will the international benchmark for perfection in travel look like in, say, 10 years? Will it be raw speed, or will it be that flawless, effortless experience?
That's definitely some food for thought for your next journey, whether it's aiming for 18 seconds of delay or 1,000 kilometers an hour. Thank you for joining us for this deep dive into the world's fastest trains.